Good afternoon, ladies and gentlemen. My name is Anna Bacher and I'm Austrian. I'm CTO and ethical hacker. My career started 20 years ago in a corporate world where I've got relevant cyber and technical experience working for IBM, Accenture, and Temenos. Throughout my career as a security architect, I've been in a unique position to innovate in the fields of network security, endpoint protection, security analytics, and threat defense. I co-founded 2 companies, and I'm also a co-author of the patent for peer-to-peer network security. Since January 2018, my team and I worked head down on a solution that tackles one of the trickiest issues of analyzing software applications, that of finding, prioritizing, and repairing the worst-case vulnerabilities. And today I'd like to share with you our experiences and roadblocks by applying latest research innovations in natural language processing to the area of detection and remediation of security vulnerabilities. According to Juniper Research, The Future of Cybercrime and Security 2019, the total cost of cybercrime is expected to exceed $2 trillion this year. According to Juniper, this is a 4-fold increase when compared to the estimated cost of cybercrime in 2015, just 5 years ago. Attackers weaponize AI. On the bottom of this slide, you see the major releases of open source machine learning libraries and frameworks. And at the top of the slide, you see that every major machine learning release is closely followed by a new attacker's kit, starting in the early 90s, followed by ML-based toolkits that add obfuscation, anti-decoding to evade detection, polymorphism to evade antivirus, deliver extremely volatile and dynamic payloads to avoid detection by network intrusion systems, and finally, a fully automated kit that can detect user environment and deliver specific and targeted exploits. We are in the era of weaponized AI. Today, I would like to draw your attention to weaponization of AI based on the latest research breakthroughs in the field of natural language processing. And why is this field? Because natural language processing research got the advances in the past 2 years that will be certainly used as emerging attack vectors. It's fair to say that the turning point for the advances in the natural language processing was 2017, when the transformer network was introduced by Google in Attention is All You Need paper. And in this paper, Google showed that transformer outperforms other neural networks on academic English to German and English to French translation. And on top of higher translation quality, the transformer requires less computation to train and is much better fit for modern machine learning hardware, speeding up training by up to an order of magnitude. Since then, the researchers apply this architecture and others to successfully train models for a variety of tasks, including speech recognition, text generation, detection of vulnerabilities in source code, and others. On this slide, you see the simple neural network architecture during the training. Same architecture and training process can be applied to different input data, such as you see here, text, voice, programming code, and others. But for every positive development in natural language processing comes a negative one. Advances in speech recognition turn fake voice into an increasingly successful attack vector. Advances in text generation feed fake news attacks. Advances in AI-based vulnerabilities detection used to feed AI fuzzers attacking applications. Based on security company Pindrop research in 2019, 90 voice fraud attacks occur every minute. And the weaponization of AI made fraud attacks times less costly and more efficient. One of the notable attacks in 2019 happened when criminals used artificial intelligence-based software to impersonate a chief executive's voice and demand a fraudulent transfer of $200,043. The CEO of a UK-based energy firm thought he was speaking on the phone with his boss, the chief executive of the firm's German parent company, who asked him to send the funds to a Hungarian supplier. The caller said the request was urgent, directing the executive to pay within an hour. The UK CEO recognized his boss' slight German accent and the melody of his voice on the phone. And the CEO made the requested transfer to a Hungarian supplier and was contacted again with assurances that the transfer was being reimbursed immediately. Cybersecurity company CHAQ conducted research with the University of Baltimore, which found that the epidemic of online use now costs the global economy $78 billion annually. The report also estimates fake news has contributed a loss in stock market value of about $39 billion a year. And these figures will be probably increased by multiple fold due to the very important research event that happened in November last year, 2019. The research lab OpenAI has released the full version of their text-generating AI system called GPT-2. GPT-2 is part of a new breed of text generation systems that have impressed experts with the ability to generate coherent text from minimal prompts. The system was trained on 8 million text documents scraped from the web and responds to text snippets supplied by users. Feed it a fake headline, for example, and it will write a news story, fake news story. A researcher used an AI-based password cracking tool to uncover over 40 million passwords leaked in an attack, all of which was created by real-world users. What he did, he ran a tool on NVIDIA Tesla K80. So it's a GPU card with 4,992 cores that you can rent on Amazon Web Services for $90 per hour. And the AI model used on the tool can calculate approximately 800 million SHA-256 hashes per second. That's nearly 3 trillion per hour. So 20 hours later, with the expense of $18, 11 million password cracked. By brute forcing before AI, it could have taken many, many years. Fuzzing. Fuzzing is an automated vulnerability discovery technique by feeding manipulated random or abnormal inputs to a software program. Fuzzers works best for discovering vulnerabilities that can be exploited, like buffer overflow, denial of service, cross-site scripting, and SQL injection. These schemes are often used by hackers intent on breaking the greatest possible amount of damage in the least possible time. So typically before AI, a hacker fuzzing Internet Explorer, for instance, might run Microsoft's browser in a debugger tool, so they can track every command the program executes in the computer's memory. And then that point the browser to their own web server, one designed to run their fuzzing program. And that fuzzer would create thousands or even millions of different web pages and load them in its browser target, trying variation after variation of HTML and JavaScript to see how the browser responds. After weeks or months of those automated tests, the hacker would have logs of the thousands of times the browser crashed in response to one of the inputs. And before AI tools, those automated tests would take many months before the hacker would have logs of the thousands of times the browser crashed. Typical AI-based fuzzers consist of two components, a vulnerability prediction model and vulnerability evolutionary fuzzer. So this is what you see here. The prediction model will perform an analysis on which components of the software are more likely to have vulnerabilities. And then the fuzzer will leverage the prediction information for the targeted attack. So here I covered some emerging attack vectors based on NLP research. Coming back to an attack vector based on vulnerabilities in the application source code. Based on Positive Technologies Report 2019, 82% of web application vulnerabilities are in the source code. How does it affect the enterprises? Capital One Financial Corporation, the fifth largest US credit card issuer, said on 29th of July that a hacker accessed the personal information of approximately 106 million card customers and applicants, one of the largest ever data breaches of a big bank. alleged hacker, a former employee of Amazon Web Services, got arrested. So this attack became possible due to the vulnerability in the Capital One web application firewall software. The type of vulnerability exploited by the intruder, called a server-side request forgery, in which a server can be tricked into running commands that it should never have been permitted to run. So, and as a result, 106 million records stolen. On May 24, 2019, the website for Fortune 500 real estate insurance giant, First American Financial Corporation, leaked hundreds of millions of documents related to mortgage deals going back to 2003. The digitalized records, including bank account numbers and statements, mortgage and tax records, social security numbers, wire transaction receipts, driving license images, were all available without authentication to anyone with a web browser. The attack got possible due to the software vulnerability called insecure direct object reference. It's very simple. Anyone who knew the URL for a valid document at the website could view other documents just by modifying a single digit in the link. So how then the defenders, how do they defend the application code? So they use non-AI rule-based security application testing solutions. So those rule-based solutions means that they lag behind attacks and they have a reactive nature. They typically miss out based on their multiple benchmarks, 60 to 90% vulnerabilities. So some of them are almost unusable. They do not find zero-day attacks, and they do not provide automated fix suggestions. So it's really time to use AI to protect applications, to catch up with attackers. And today, I'd like to demonstrate to you how my research team trained the machine to detect vulnerabilities and to write security patches with higher precision and confidence. So the model is trained based on more than 90 million commits from about 3,000 cyber databases. Using real-world data is an advance on the current crop of static analyzers that rely on hard-coded rules to detect exploitable vulnerabilities in software. And one of the biggest benefits is its ability to learn the patterns of vulnerabilities just from examples and provide automatic security patches. So how did we achieve it? I have a question. What do you think is common in a cat and programming code? I prepared several quick answers for that. So first is the programmers love cats. GitHub has a cat as a logo. Second, cybersecurity researchers keep finding cats, whether they like it or not, while trying to predict whether a mobile phone has a software running to start a terror attack. Maybe there are more answers that you can find yourself. In the context of my today's presentation, this slide is the key to understand how we apply deep learning to a source code for detecting and remediating vulnerabilities. What's common is how a cat and code are treated by deep learning networks trained for image recognition or vulnerabilities detection tasks. As you probably know, the deep learning is successful in the domain of image processing and other applications, but they are different from the domain of vulnerability detection. In order to clearly see the gap between these domains, let's see the example of using deep learning to detect a cat in the image. This can be achieved by the notion of so-called region proposal and leveraging the structural representation of images, which is texture, age, and color. Multiple region proposals can be extracted from one image, as you could see here, and each region proposal can be treated as a unit for training neural networks to detect objects, for example. When using deep learning to detect vulnerabilities, there is no natural structural representation for programs like what region proposal is to images. So that means that deep learning cannot be directly used for vulnerability detection. To bridge the gap, one may suggest treating each function in a program as a region proposal in image processing. However, this is too coarse-grained because vulnerability detectors not only need to tell whether a function is vulnerable or not, but also need to pin down the location of vulnerabilities. So we need the fine-grained representation of programs for vulnerability detection. On the other hand, one may suggest treating each line of code, like for example, statement, as a unit for vulnerability detection. And this treatment has also two drawbacks. First of all, most statements in a program do not contain any vulnerability, meaning that few samples are vulnerable. And second, that multiple statements that are semantically related to each other are not considered as a whole. So inspired by the notion of region proposal and image processing, we divide the program, as you could see here, into small pieces of code, like number of statements, which may exhibit the syntax or semantic characteristics of vulnerabilities. With a region proposal idea in mind, we started our journey from reading the latest researches in applying NLP algorithms and deep learning in the area of application security. And we came across this research published by Draper and Boston universities in 2018. So the biggest breakthrough of this research is the demonstration of potential of using machine learning and deep learning to detect software vulnerabilities directly from source code. And as part of the research, they showed advantages of ML methods over traditional static analysis tools. One advantage is that their custom lecture and models can rapidly digest and score large repositories and source code without requiring that the code be compiled. Additionally, since the ML methods all output probabilities, the thresholds can be tuned to achieve the desired precision and recall. And the static analyzers, on the other hand, return a fixed number of findings, which may be overwhelmingly large for huge code bases or too small for critical applications. So the second advantage is that we can use visualization techniques such as the feature activation map to help understand why algorithms make their decision. Our reproduction of Draper and Boston universities model is very close to their original. And their best performing model is a convolutional neural network, as you can see on that slide. So this is how it works. Input source code is lexed into a token sequence of variable length. Then it's embedded into representation, filtered by a number of convolutions, and max pooled along the sequence length to a feature vector of fixed size. The lone feature vector is used as input to a random forest classifier, which improves performance compared to the neural network classifier alone. The major difference between our model and Draper and Boston University's model that explains the better results you see on the slide is it in the notion that Draper analyzed every single function without context. So it means basically that multiple statements that are semantically related to each other are not considered as a whole. And second, it means that vulnerabilities that go beyond a single function are not found. And during our experiments and tests, we learned that those vulnerabilities are above 90% of all vulnerabilities. For non-data scientists here, there are a couple of KPIs which are typically used. One of them is MCC, which is a Matthews correlation coefficient, is a correlation coefficient between target and prediction. The highest value is 1, so the higher value, the better. So the less difference between target and prediction, the better. Precision here refers to the percentage of predicted results which are relevant, and recall refers to the percentage of total relevant results correctly classified by your algorithm. And F1 is a function of precision and recall. And as you can see here, so all functions, the higher the number, the better. So the closer to 1, the better. And as you can see here, for our model, we achieved above 90% on all major KPIs. To achieve these results, we added semantics, code semantics, by creating a multiple layer presentation of each unique code version. including the various levels of abstraction, so-called code property graph. So our multi-layered code representation depicts abstract syntax trees, control flow graphs, program dependency graphs, and directory structures. And this unique insight provides our detection training with the granular detail and deep understanding of all data flows. And with these optimized views, both false positive and false negative are greatly decreased approximately by 10 times, providing accuracy at an unprecedented speed and scale. So here you see a couple of KPIs. FPR is the false positive rate. It's basically detected vulnerability, which is not vulnerability at all. So our model achieved about 3%, while the industry or research standards for non-AI based solutions is about 20 minimum. False negative rate is the missed vulnerabilities. So those are dangerous ones. Our model achieved about 5%. And as you could see, the open source and other and commercial versions, rule-based industry standards, it's about 55 up to 85%. 85% means that the solution is actually not usable. And then you also see accuracy, precision, and F1. This is the same what you've shown you on the previous slide. And here you see also that there is a much lower numbers for the rule-based industry standard than for our AI-based model. So now detection results were good. And what about vulnerabilities remediation? It took an average of 38 days for an organization in 2018 to remediate a vulnerability. And this is based on one of the researchers, after analyzing more than 360 million security incidents. So we asked ourselves a question: can we provide real-time remediation suggestion to fix vulnerability within minutes and not days? And we came back to the NLP research, in particular to the transformer architecture, and ask ourselves whether transformer can be used for vulnerabilities remediation. So we decided we can have a goal on that. So we took the problem. We look at this problem of learning to automatically repair the source code of software containing security vulnerabilities, as it is similar to grammatical error correction, in which a grammatically incorrect sentence is translated into correct one. In our case, bad source code that contains a vulnerability takes the place of an incorrect sentence and is repaired into good source code. We also noticed that transformer was used in different text-related tasks. So here you see the text generation task, and the key for transformer success is the attention mechanism, as you see here. The attention mechanism looks at an input sequence and decides at each step which other parts of the sequence are important. So let me clarify with an easy example. When reading, for example, this text, you always focus on the words you read, but at the same time, your mind still holds the important keywords of the text in memory in order to provide context. We noticed also that in 2019, transformer was already successfully applied in a programming for the programming language in a task for code auto-completion. So here you see how it works for the programmer. When programmer writes a code, he has automatic suggestion with a probability of confidence on how he should finish his line. Our first model was based on the BERT architecture, which you see here. This is encoder-only part of transformer. And BERT stands for bidirectional encoder representations. The consideration of applying BERT to the vulnerabilities remediation task was its breakthrough in grammar correction tasks. So we started training with a goal to teach a model to learn a whole code fix at once. As the work on the model progressed, we realized that the model, even very robust one with multiple hidden layers and hundreds of thousands of different parameters, could not learn to predict the whole code. So the model was overfitting, meaning that it couldn't predict accurately the code fixes for vulnerabilities examples the model hasn't seen before. Also, the training process hasn't progressed well. The loss wasn't decreasing, and after tuning and adding more parameters to the model, it became clear that the model is not robust enough to learn. So we decided to switch to a technique and train a model to predict not the whole fix, but only one token at a time. And this approach showed better results. So through a number of countless iterations, we saw that the gradients were flowing and the loss was decreasing. So we thought finally that we made a good progress. However, those great results were due to a bug in a PyTorch library. So when the prediction started, instead of that gives the 99% errors on validation set, and then came predictions, and which is all zeros, as you could see. So the model was not have not been able to learn to predict anything. So then we debugged 2 versions to find what's happening and found out that for masking look ahead matrix was transposed in Python version, PyTorch version. So in practice, which I showed you on the previous slide, it was looking forward instead of looking backward. So it meaning that the model did not need to learn to predict the next token based on the history, but instead it just saw the next token. So this is the cheating. And finally, after countless iterations, we arrived at an efficient model for vulnerabilities remediation. The transpose matrix here is also correct. So you see this is looking backward. So we'll start it. And allows the model to learn knowing the previous context, so knowing their historical tokens. And so we also introduced some additional KPIs. Which we call absolute error and relative error. So absolute error is percentage of tokens that predicted with errors. So difference between output and patched version. Then we introduce the notion of required change. So required change is percentage of tokens that is changed between patched and vulnerable versions. And relative error is absolute error divided by required change. So it's basically difference between vulnerable and patched version. If relative error is more than 100%, then transformer is adding more errors to original code, then it fixes it. If relative error is equal to 100%, then it means that model performs not better than just predicted input as output. And if relative error is less than 100, then the model is actually fixing something. So our best model arrived at 1.4% relative error and at 0.24% absolute validation error. And now the model is working, so you can find and remediate vulnerabilities in your own code. The code is highlighted, the vulnerable code is highlighted, the fix is automatically shown and can be applied in real time, and scan can be redone. Our model is also available via the integrated developer environment plugin, so this is very similar. Okay, now models are working, but is there a danger that a hacker can attack vulnerability detection model and falsify the output? And the answer is yes. So there are several major attack vectors, and one of them is visualized on this slide. So the attack vector here is so-called evasion and poisoning attacks. It's a generative adversarial attack based on generative adversarial networks. The aim of the attack is to generate fake samples similar to the training set, having almost identical distribution. And why it is dangerous? First of all, confidence reduction. So the attacker tries to reduce the confidence of prediction for the target model. In case of vulnerability detection, it means critical severity vulnerability can be predicted with a lower confidence and won't pass the threshold and won't be shown to a developer for fixing. And the second is the mixed classification. So the attacker tries to alter the output classification of an input example to any class different from the original. In case of vulnerability detection, vulnerability that belong to the critical severity class, such as, for example, buffer overflow, may be misclassified as less severe class and will be pushed as low priority and not fixed. So what could be the defense strategy? Interestingly enough, the defense strategy can be based exactly on the same generative adverse networks, which is used in this example as an attack strategy. So the defense gun aims to leverage the power of generative adversarial networks to reduce the efficiency of fake perturbations. So in typical gun, a generative model which emulated the data distribution and the discriminative model that differentiates between original and fake input are trained simultaneously. And the centralized idea here is to project input file into the range of generator by minimizing the construction error prior to feeding the file to the classifier. Due to this, the legitimate samples will be close to the range of generator than fake samples, resulting in substantial reduction of potential adversarial perturbations that can affect the model's output. So we see that the human attacker can be successful in attacking an AI model. Can AI become an attacker itself? To conclude my today's webinar, I'd like to talk about an ongoing concern voiced by many prominent tech entrepreneurs and researchers regarding the dangers to human society posed by AI. As Elon Musk put it, as AI gets much smarter than humans, the relative intelligence ratio is probably similar to that between a person and a cat, maybe bigger. I do think we need to be very careful about the advancement of AI. During our work, we came across an interesting phenomenon. One and the same pre-trained model tested on the same geographical machine and the same vulnerable files sometimes produce different results. In some cases, the model made minor changes in code highlighting. In some cases, the model changed its mind on detection confidence, decreasing or increasing the confidence. And in some cases, the model changed its mind on whether vulnerability exists or not. The range of changes we noticed were in between 5 to 20%. In real life, it would be same as that if you ask me a question and I give you one answer now, and I will completely change my mind in 2 weeks based on some moods and provide you with another answer. Before graphical machines and the neural networks, machines always were deterministic in the answers. It means that if you ask one and the same question, you will always get one and the same answer or result. In the current times of AI, machines became non-deterministics, as we've noticed. It's almost like they have their own mind and change it from time to time. So as AI applied to cybersecurity, at some point, we will also believe in trained machines that are so much more competent than we are that the slightest divergence between their goals and our could make them oppose us. What do we do to better control AI? From experience we made so far, I would say try to understand and visualize AI decision-making process and try to make AI output deterministic. Here are a couple of conditions we shall make right. Making deterministic GPU infrastructure, deterministic ML frameworks, and use atomic operations with care. Thank you very much for your attention.